Good morning, hackers. It is bright and early my time. I think I mentioned that in my Discord announcements. But thank you so much for tuning in today. If you are tuning in from somewhere really cool, feel free to drop in where you're tuning in from. You'll have to pardon me because I'm probably going to be yawning a few times just because I'm not quite used to waking up this early just quite yet. Usually I sleep in for another hour-ish before I get up and do anything productive. So yeah, here we are. Um, if you are new to this workshop series, this is the Nature of Code series where we build natural systems using computer science. In particular, we are using the P5 JavaScript animation library, and this is what we built yesterday on stream. We built this sort of circle moving around kind of things going on. But instead of the usual, I guess, um, setup where we would run and change the circle manually inside the sketch.js folder right here, we are making it so that we can use this very new and fancy um, library, not library, class objects that's known as vectors. And so last time we did this, I forgot to actually pull up our whiteboard. We pull up the whiteboard, yeah. We were learning about how matrix addition works as well, matrix, vector math works in general. And so one of the ones that we covered and implemented ourselves was vector addition. Well, I guess we didn't really implement it, but we were really just like using it. And then we also talked a little bit about how the canvas inside of P5 kind of flips the y-axis axis, not access. So as y gets bigger, the object on the screen moves lower and lower on the screen, whereas as the x gets bigger, it moves more and more to the right. And then we also talked a little bit about how animation frames work, where all we need to do to figure out where the object is going to be in the next frame is just add to the direction or add to the next frame the speed at which we had moved. And so that's what we were talking about right over there. So right up, uh, as of now, we are right around halfway, just a little over halfway through the chapter on velocity. Hopefully, we'll be able to spend the extra time that we have on actually building a rather cool project. If you haven't already, though, I want to make sure that you all have a chance to check in right over here. Whoop, wrong page. Right over here. And let's see. Oh, I haven't posted the link yet. The link is right over here. And if you need it, we also have the QR code in the top left corner, just floating right above my head. So if you have any questions about what it is that I'm doing, feel free to drop them in chat. I am more than happy to tell you all about the wonderful things that we're going to be doing today. But yeah, let's get started. So I was thinking last time we kind of played around with this when we made it, we found out that this thing's kind of like moving relatively consistent between runs. So that means as soon as we initialize it for the first time or create an instance of this object, it always moves at the same speed, which is totally fine if we've only got one. But since we created a whole class for this, which is hidden under mover.js, I was thinking it would be cool for us to just spawn like a whole bunch of them. And then we just keep track of all of them. And that way we can see the just like collision of all these random, not necessarily collisions. That is a separate thing in computer science, animation, and games and such. But rather, um, just like having a whole bunch of random stuff. Random stuff. There's not so much random. A whole bunch of movers on the screen. So I guess real quick, I'm gonna do a quick code tour of what's going on over here. we have a constructor class. This is the thing that runs whenever we create an object for the first time. So whenever we make a mover for the first time, the first thing we're going to be doing is we're going to be creating a attribute known as this dot position. And this position is going to take a vector that has a random value between the width and the height. And this is basically just going to ask it to spawn somewhere within this rectangle or square. This next line is the thing that's in charge of the velocity. So this is how fast this thing goes and in what direction it goes. We covered how vectors have two attributes. That is the magnitude and then the direction. So the magnitude is how fast, and the direction is where it's going to be pointed. And so we've got two values right over here, which is being selected, -2 and 2, and then also from -2 to 2. Next up, we've got the update function, which doesn't do a terrible lot, but this is really important because this is the thing that's responsible for actually making sure that our thing moves between frames. We discovered also yesterday that this animation plays at a crispy 60 FPS. I don't know that you're going to be getting the same speed since you're watching this on a stream, but if you were to run this on your own computer, it would be about 60 FPS. Now you should be able to run this by checking out this link over here. Just keep in mind that if you want it to be a live update, you'll have to probably refresh your page. And if you want to make your own changes and save it, you'll probably need to log in. I am personally logged in using my GitHub account, which just basically makes sure that you always have access to all of your old projects. So I have access to all of these things. These are all the things that I played around with while using P5. Okay, next up, we've got the show function. So the show function is responsible for actually drawing the circle that we have here. And so we've got the stroke, and the stroke is just going to describe the color of our circle. And so we wanted to make it a nice light color. So we made it at 255. It is from 0 to 255, where 0 is the darkest and 255 is the lightest that it can be. And then we gave it a fill of with the RGB values of 100 red, 150 blue, sorry, 150 green, and 255 blue. Then finally, we just asked it to draw a circle at this position X, this position Y, and then the radius right there. Okay, I guess there's one more thing that we can do here, which is to add a stroke weight, and this is how thick the stroke is going to be. So I'm just going to go with a nice value of 4, and you can see here that we've got a thicker stroke around our circle. All right, final function. This is check edges. So basically, this is just a bounds check to make sure that our circle always comes back and respawns, basically, whenever this thing leaves the screen. And so this is checking our x bounds, the upper bounds, and then the lower bounds. And this is checking the upper bound and lower bound for the y position. So that's basically all that's going on inside the mover class. And so what's going on over here is we just create our canvas, which is the thing that makes the, I guess, the square that we're painting in. And then we create a new mover. And then this draw function is something that runs every frame. So this runs 60 times per second, whereas the setup function runs once just at the very beginning. And then we just go ahead and run through the rest of these. Okay, so that's pretty much the rundown of what we did last time. Now, to kick things off, so we can get more familiar with what it is that we're working with, I was thinking it would be fun to just spawn a whole bunch of these movers. So every time we run this function, we'll see that the mover changes direction. So I think it would be really fun if we could just make like 10 of them spawn and just see where they end up running off to. So first thing I want to do is I want to make an array. So this is just going to be a group of movers. And I believe the way we can do that is okay. Um, I've forgotten how to do JavaScript arrays. The nice thing about P5 is that it is just a JavaScript library, which means we do have access to all of the JavaScript functions that we would normally be able to take advantage of if you were doing some form of like web development. So what we want to do is we want to look up how to create a JavaScript array. Don't mind me being bad at computer science and completely forgetting how to do this. So it looks like what we can do is we could just set it to be equal to square bracket. So let's go ahead and do that. I thought that's what it is that I did earlier. I'm not sure why that was giving me an error. Or maybe it's because, I was doing it like Java style, where you can just put the square brackets without assigning it to be the other thing. Anyway, let's rename this to movers dots, and then we can add in a new mover just like this. So you don't know what the push function does, and it basically treats the array like a stack of plates. And so what we're doing is we're just pushing something onto that stack. Um, and I guess what we're doing is we're just creating the very initial stack. But what we want to do is we want to actually create a stack that's about 10 plates high. Let's start with that. So what I'm going to do is I'm just going to do a nice let I is equal to 0, I is less than 10, I plus plus. And then we're going to go ahead and pop this right into here. And then the next thing that we want to do now that we have created our movers is we want to actually be able to update all of them. So what we can do is we can do a for mover, let mover. Actually, I forget how to do the for each loops inside of JavaScript. I guess for each is a separate thing than what I'm looking for. I'm looking for the enhanced for loops, which allows us to, I guess, just like kind of do for everything inside of this data structure. So we're gonna look up how to do that. JavaScript for every element inside an array. Let's see. For each, there are a couple ways to do this. This is the way I was looking of doing, where we define a variable that represents the individual element of our array. The other option is to define a function where we can do that instead and literally call for each, then run this thing on it. And this is the most simple way to do it. This is the way that we would normally, I guess, kind of do it with the um, this is the naive way of doing it. I guess. Oh, I don't need to describe it this much. So let's go ahead and call this mover for mover in movers. We're just going to go ahead and copy this over. Okay, so this should spawn 10 movers and then update each of them every frame. So let's go ahead and see if that works. We are running into a problem. Let's see what this problem says. Mover.update is not a function. Verify whether mover has an update function. How curious. So I wasn't expecting that. My guess is let's actually just double check to make sure That update is indeed a function. Yes, it is. So then the next thing I want to check is whether or not this thing is actually showing up as a mover. So I'm just going to go type. I don't remember how to do type in JavaScript. I always confuse it with the Python syntax. So I'm going to look up how to do types in JavaScript. It is the type of operator, and it is a unary operator, which means we only need one argument for it. So if I just do type of and then space mover, we should be able to see what type this is. It is currently a string. That is not ideal. Okay, so now we need to understand why this thing is showing up as a string. I want to actually see what happens if I just print out mover. Okay, so it says it's being printed out as a value of 0. Okay, so I suspect it's because of the way that we created this array and added to it. Maybe it's the fact that we did push. So let's look up JavaScript's array. Let's revisit this. If anybody in the chat is a professional JavaScript person and knows how to solve this problem, feel free to hop in. Otherwise, I'm going to bumble around until we can figure this out. Well, I guess what we could do is instead of using the push function, we could just manually assign the movers into this. So what we can do is we can do movers I is equal to new mover and just do that. Still not working. How problematic indeed. So I'm going to pop in here and just see if there's anything funky going on over here. I don't think there is. Okay, so here's what I'm going to do. I'm going to comment out all of this stuff. And we're just going to see if we could just manually set a couple variables for movers and just see if we're allowed to have multiple. Let mover exist. Let mover 2 exist. Okay. Mover 1 is equal to new mover. And then we just want to run mover.update. And then I'm going to copy that over, and we should have that. Okay, so we can in fact run everything one at a time, but for some reason it gets converted into a string whenever we put it into the array. JavaScript array turns everything into a string. Both are objects. So the thing is that we're not trying to convert things into a string. What we want to understand is why are my JavaScript objects turning into a string? Concatenation, so if we're doing any sort of string math, we're using HTML elements. If we are converting it, I don't think it's any of those things. Hmm. Was not anticipating starting off today with a bug on the very first thing I tried to do. Let's go ahead and hide the things that we did before, then unhide the other things we tried to do before. I suspect maybe it's the way that we were doing this loop. So perhaps instead of doing for movers in movers, let's do this the old-fashioned way. Let I is equal to 0. I always forget JavaScript array length. Yep. Okay, so it is in fact just a property. I plus plus. And then because I'm lazy, I'm just going to set movers equal to movers I instead of changing all of the stuff that says movers down here. Let's go ahead and try that. Okay, so that did actually work. It's lagging a little bit because of all of the console logs, I suspect. Yeah, there we go. So there we have it. It might actually be doing a little too much math, which is weird because I've definitely done this kind of simulation before, but instead of drawing a bunch of individual objects like this, I actually added in collision before, and it seems to be fine back then. Maybe it's just my computer slowly catching up. But yeah, if we wanted to, we could actually give these all a little bit more direction to make sure they all flowed in the same direction. So what we can do is we can pop into the initial creation, and instead of choosing -2 and 2, we could do something like changing the range from 0 to 2 to 2. So then it should move diagonally from the top left over to the bottom right. There we go. So yeah, I don't want to say that we've created a particle system quite yet, but it's getting pretty close. Anyway, let's actually continue going on through the textbook. So this code bit right here was basically just the very same thing that we've already made actually over here. We just made the mover file in another class, or sorry, in another file instead of putting it all in the same file. But if we wanted to, we could have technically defined mover inside of sketch.js. I was just doing this because organization is important, especially as things get big, and it's good to practice good organization before things get that far. So here we go. If OOP is at all new to you, OOP being object-oriented programming, which is the thing that we use that describes the reason why we're doing all of these class situations, this whole class thing, because that allows us to create an object, and everything is about manipulating that object in some way. So let's continue reading along. Let's see, he spends the beginning talking about the vector class, and this class is a template. So what are these objects doing inside of another object? Because position, or I guess the vector class is technically an object in itself. He says this is actually quite a normal thing to do. Objects just hold data, which can include other objects. This is going to happen again and again. Soon we will be writing a particle object, but that is going to be 3 chapters from now because we are currently in chapter 1. Very exciting. We've actually gotten a taste of what that's going to look like. So, you may have noticed in the mover class, setting the initial position of velocity inside the constructor without any arguments, but we will be exploring what happens when we actually add arguments to the constructor. When he's talking about arguments to the constructor, basically right now inside of our parentheses right here, we don't have anything inside of it, but if we wanted to add arguments, we could have added in a number here, maybe to help set the initial value. If we didn't want it to be random and then we instead wanted it to be a bit more I guess, like structured in relation to each other, or in relation to other objects inside of the array. But since we don't have any arguments, we're not going to worry too much about that. Perhaps if we finish this chapter a little bit early, we can explore what that looks like. But for now, let's continue going. Let's see. We're going to be starting to jump a little bit more into the physics side of things, or I guess the physics and mathy side, where we talk about acceleration. So, acceleration is something that describes the rate of change of velocity. Before, we had defined velocity as the rate of change of position, and so acceleration is just how fast the velocity changes. All right. So if we wanted to add acceleration, we could take the velocity and add it like that. And then actually add our velocity. So this is going to be a two-step process now. As an exercise from this point forward, he's going to make a rule for himself. I guess I should talk about real quick who this he is that I'm talking about. The he in question is the author of this book, which is Dan Schiffman. He's a professor who wrote the book that we are reading today. Very cool guy. He runs his own YouTube channel that's called The Coding Train. I'm going to quickly show you what this looks like. Yeah, this is the man himself. This is the guy who wrote The Nature of Code. He actually has his own YouTube channel as well, or I guess like series specifically on the nature of code. We are doing things a little bit differently and just going straight from his book. But if you would prefer an alternative teacher than doing things on stream with me, definitely go and check out his book. Or I guess his streams. He does things a little bit faster than me. But yeah. Anyway, let's keep on going. So he's going to be talking about how to calculate acceleration. There are a few ways, a few different types of accelerations to play around with: constant, random, and acceleration towards the mouse. And it looks like he's going to go through the different kinds of acceleration. So, initialize a stationary mover at the center of the canvas. All right. This is pretty much just making it so that they always spawn in the middle for their initial one, and then it doesn't move at all. And then we're creating something that also doesn't move. For some reason, this acceleration isn't adding anything. Here we go. So this is adding in acceleration from .001.01. So that would make it pretty fast eventually. Let's go ahead and try adding that into our current sketch. So what we're going to do is we're going to pop into constructor. We are going to comment this out just for the sake of making it easier for us to go back to our old version. Okay. And then what we're going to do is we are going to create vector, and we're going to set this to 0. All right. Then the next thing we're going to do is we're going to add acceleration. Create vector, and then we're going to set this acceleration to be a I actually rather enjoy having it go from right to left, so we're going to continue going in that direction. We're going to start by putting this like that, and so that should be pretty similar to the values that he had. But to make sure that we actually have some variety to the acceleration, I'm actually going to set this as a random range. So let's set this to that range. Range from 0.001 to 0.01. That should be just enough variety. Okay. And then we need to make sure we actually end that. So I guess to make this a little bit more readable, let's actually go in here and put these two on new lines. There we go. Hello, good morning. Hope you are well as well. All right. So, looks like things kind of started off frozen. Ah, you know why? It's because I forgot to actually change our update function. So what we need to do is, in addition to adding the velocity, actually right before that, we need to go to this dot velocity dot add this dot acceleration. There we go. For some reason, this thing I think it's only looking like that because yeah, weird formatting things because the screen was a little small. Okay, there we go. So now we've actually added in the acceleration, so these things are all going to be speeding up. Just like if we were in a rocket jet that was slowly getting faster and faster. So yeah, looks like we were able to do that just fine. Very cool. I'm gonna stop this because I think the moving screens is a little fast for me. Maybe let's add a limit to how fast the velocity can get. Mm, I don't remember how to do the velocity math. Um, because I guess there is an x and y coordinate. So what we could do is we could do a comparison to see if the velocity dot x and the velocity dot y ever exceed a specific value before we add this thing. So let's go ahead and do that actually. So we're going to set a constant. We're going to do things in the clean coding. I'm going to try to adhere to some clean coding standards. And to do that, I'm going to be creating descriptive booleans. And so first thing we're going to be doing is we're going to be checking to see if x velocity is greater than this dot velocity dot x. We want to make sure that this is less than, let's call it less than 10. X velocity is equal to, whoop. We want to actually make this next one y velocity. It's also less than 10. Okay. And then max. Let's set this to be max. And then what we can do is if the x velocity max, or actually, according to clean coding standards, we should be doing is we should be putting the variable part of the comparison on the left side. Actually, we've already done that. We've put that on the left side, and then the static side, the thing that doesn't change, the thing that we're comparing against, stays on the right side. So we're actually already there. So all we need to do now is just put this in here. So now what we're saying, if it has exceeded the x velocity max or the y velocity max, then we will not add the acceleration. So I guess what I could do is pop this right into here. And if we wanted to make sure that it does happen, well, actually, I guess we want to make sure the opposite happens, huh? So what we should do is actually, um, there we go. Okay, so now we actually have a positive instead. I think one of the other clean coding things is to make sure that whenever you do comparisons, you're checking to see like if something is true rather than if something is not true. Because you're checking if something is not true, then it just like adds more complexity unnecessarily, and it's like a really easy thing to be able to trim. So all we're doing is we're just checking to see maybe we should be a little bit more descriptive. Can add. So now it should accelerate up to a certain point until it gets to about 10. So we can wait and check to see once all of these look like they're moving at around the same speed. Some of them are a little bit slow on the blooming side. But of the fast ones, they look to be right around the same speed. So yeah, I think that's a good exercise in programming for now. Let's continue on with the book. The only missing piece is to get the mover moving. We've actually already taken care of that. Yes, that was by adding in the acceleration and setting that to be an initial value. We set it to be a random value from a range. That way we would have some variety as far as how fast these things start moving at least. So there actually is a limit function. We could have just done that instead of doing all of this math stuff. So let's go ahead and try doing that. Instead of doing all of this, I'm going to take this function or this call out and then delete the rest of this. And then let's see why this thing's complaining. Oh, it's because I didn't copy it right. Okay, so the function still works. I'm assuming we can kind of put this wherever. So we should probably just put this after the addition happens. That way it happens right before it's actually added to the frame. And because this last function call is the one that actually, I guess, like draws the new location for the circle. So if we want to have a limit, we want to make sure we enforce that limit before we actually get to that stage. And so this sounds like it's going to do the same thing that we just did. Let's go ahead and check that. Let's actually set this to a smaller limit of like 3. That way we will hit the limit faster, and once all of these look like they're moving around the same speed, we'll know it worked. Looks like they aren't getting much faster than what they are now, so yeah, I think that is a lot more elegance than doing the other way around. So I'm happy we found that. All right. So what is the magnitude of velocity? If it is less than 10, just leave it as is. However, it is more than 10, reduce it to 10. That is exactly what we did. Write the limit function for the P5 vector class. We've actually already done that. Oh. But that was a lot more elegant than the way that we did it. um, let's see. So basically, the way that this proposal works is what we're doing is we're going to take in a value of max. Let's actually do this. We can do this ourselves, or we can copy it in. That way we can, it'll be easier to explain this way, actually. max vel, we're gonna call this. And so if this dot's mag, so this is the magnitude, which is how fast the thing is going. Um, the reason why I changed it from max to max vel is because max, I'm pretty sure, is a function name within P5, and so we don't actually want to be overriding that. We got a question in the chat. Hey Ryan, in your experience, how does learning to simulate physics and code change how someone thinks about motion in the real world? That is a fantastic question. Usually, I've been thinking about it the other way around, where I see things that happen in the world, and I'm like, I wonder how we can do that, create a simulation of it. It's kind of like if you walk around with a camera, you start seeing opportunities to take pictures all the time. This is speaking as somebody who likes to do photography. So I actually found myself thinking about it in the opposite direction. I do like the idea of thinking about it from this way going into the real world, though. Um, but usually, the things that we do in our simulations are to mimic what happens in the real world so we can better understand the real world, or we can, I guess, like try to figure out what happens to recreate something that's happened in the real world. So, something I was covering in my game design class, or I guess one of the game ideas that we were that I learned heard was basically um, the idea of doing some sort of forensic analysis and the use of environmental storytelling to try to recreate what it is that happens in a particular, I guess, like environment. So, like, if you went to a crime scene and there's like things scattered all across the tables, and then you could try to figure out, like, if the lamp fell this way and the rug is kind of torn up, what were the original order of events that you think happened? I think that's a very cool idea. Um, that's actually a game idea I think would be kind of fun to play around with inside the computer science classroom as a way of trying to figure out what the order of events that happened was. That's something that's I think is also useful in programming debugging. But yeah, anyway, thanks for the question. And I am so glad that this is super cool. I am having a lot of fun with this as well. And I am glad that you are having fun, as much fun as I am, hopefully. Anyway, let's continue trying to copy down this code. So this next bit, this normalized function, basically just reduces the magnitude from wherever it is all the way back to 1. And then what we're going to do is we're going to add mults to the max. And so after we reduce it down to 1, we're going to bring it back. We're going to multiply that now unit vector, which doesn't have a which has a magnitude of just 1. It's going to multiply it back to the actual max value. So we pop this back in, and then what we can do is, I think we just run this dot limit, and then the max value of like 3. And if we rerun this thing, it should work. It did not work. Why is this not happening? This .mag is not a function. That is probably because... So we can't actually call this .mag because we don't have a function that's called this .mag. It is basically checking to see if we have something like this. But we didn't because we only can run this on velocity. Sorry, on vectors. So what we can do is we could say this dot velocity dot mag. That should work. So now things are running again, and then it crashes. So what we would need to do is we would do the same thing. Okay, cool. Yeah, so basically normalize and bolts, these are functions that actually only, and mag, that only exist on a vector class object. And because velocity is a vector class object, we can actually do things there. And if you weren't paying attention, basically, this is what it is that we're talking about. This is the velocity class object. Okay, so let's take a peek at this. Velocity and constant acceleration. Acceleration is the key. He's just basically implementing all the things that we've already done. All right, here's an exercise. This is the part where we were supposed to actually start coding, but we were following along anyway as a matter of, you know, getting in our code practice, that brain exercise for the day. So here's what we're going to do. We're going to create a simulation of the object that we want to accelerate when we press the up and down arrow keys as we move around. Okay, so I know it's probably bad to actually start by looking at the example, but I'm really curious as to what it is that he ended up doing, and it is this really cute train. But does it actually speed up? Yes, it totally does. Okay, there we go. So I'm gonna close this thing now that we've seen that example. I'm trying to figure out how fancy to be, because I kind of want to do a Perlin noise thing, but we haven't gotten to that chapter yet. Perlin noise is kind of a smooth randomness. Oh, actually, I think we did cover that in the the 0th chapter, the very initial chapter. So I think that's something that we can try doing. So let's go ahead and create a new file, run this, and make sure we have something going on. And I don't like working with a blank background or this gray background, so we're gonna spice this up a little bit. We're gonna make this a nice kind of sky blue. We're gonna go for like 210 for the blue, and let's do 100, 100. Just see what that looks like. That's actually like a midnight blue. Let's make this a little bit more green. It's not quite what we want yet. It's like an aqua green. Let's bump this up actually. Maybe a 240. Let's get a little bit closer. Maybe make this like 190. Well, I think that's pretty close to sky blue. Very fancy as always. I appreciate the fancy comments. Ah, well, welcome to the stream. You got to go back and watch part 1. Oh no. Well, we haven't gotten too far. All we've done, well, actually, okay, we've changed a few things. We have added in acceleration. If you haven't, or I guess if you want to get up to speed and do your own code tour, this is the link. Let me actually grab the link again. Let's see. Did I open? Okay. Boop, 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 boop. Pop over here. We've got our vector mover thing going on. Here. You can try that one. I can add it to the Discord after this stream if you also want to see what it is that we ended up making. All right. So we've got our sky. Now let's think about what object it is that we want to be slinging around and I guess like controlling the speed of. I'm always a fan of lettuce, but honestly, I don't think I can eat lettuce this morning. I'm sorry to disappoint the lettuce fans in the crowd. But what we can do is we can actually grab a picture of lettuce. I find it's easiest to just use an emoji. So let's go ahead and see if we can draw an emoji. Usually the way we do this is with the text function. Oh no. I appreciate the fact that you think it is cool. I'm sorry that you have no context. It's okay because we're going to be building something that will hopefully add context and I'll do my best to explain as we go along. Feel free to ask questions. Yeah. All right. So I always forget what the shortcut is to open up my emoji selector. Oh, there we go. I found it somehow. I'm going to do some lettuce, and we're just going to give it a coordinates of, well, let's put it in the middle of the screen. We know that our canvas screen is only 400 by 400 pixels wide. So if we do 200 by 200, it should just spawn in the middle. There we go. Let's make the text size a little bit bigger. Let's do like a 64. Okay. So I'm not like a huge fan of the Apple lettuce emoji, honestly. I'm much more of a fan of like the Windows lettuce emojis. This one is just too realistic. um, but yeah, that's fine. So what I've done before is I've tried to center. Actually, um, last time on stream we talked a little bit about how circles are drawn from the middle going outwards, and then rectangles are drawn from the top left going outwards. I think the lettuce emoji is actually drawn from the bottom left. I guess all emojis and texts are drawn from the bottom left. So one thing we can do to test that is we can actually just anchor this to our mouse whenever we move it on screen. And if you haven't seen this before, this is basically just a JavaScript special which takes the JavaScript's the things and puts it into a very handy dandy variable for us. So we can see that the lettuce is indeed anchored to the bottom left of it, as opposed to if we had drawn like a square. So I guess to demonstrate that, let's just quickly draw a circle. Um, let's give this mouse X, mouse Y, and then we'll give it a radius of like 64. And then we'll also do a rectangle, mouse X, mouse Y, and then we'll give this a box of about 64. Maybe let's make this one a little bit bigger. No, let's make this one a little bit smaller because we draw things in the order of going top down. So that means we always draw on top of whatever it is that we'd previously done. So if we were going to draw a rectangle, we actually need to make this one a little bit smaller. So let's make this 50 pixels. If we run this, we can see that they all have a different point of origin. A question in the chat. Do you prefer lettuce without any sauces or just plain? Depends on what the purpose of eating the lettuce is. I think I would eat the lettuce plain if I am only eating lettuce by itself. Um, and especially if I'm in a food eating competition, I would eat it plain. But if I am eating it with like croutons or something, then like I need some dressing. And especially like if you have like the lettuce in combination with other foods as like a real meal, I think it's better to just eat that with sauces. But if I'm just eating it for the sake of eating a lot and fast in a lettuce eating competition, that's when I would bring out or keep it without the sauces. Anyway, I should have actually left this thing attached to the mouse as well, so we can see how the point of origin is affected. So yeah, they all have completely different points of origin, which is something good to keep in mind. If we want to, we can actually do a static, I guess, like subtraction here. We can try to, I don't remember how the font size actually is calculated. Let's go ahead and hide these two things. So what we need to do is instead of subtracting from the mouse, we need to actually add to the Y. And if you weren't here before when we talked about that, basically the Y direction for, I guess, like digital animations generally goes from the top going down because of the way that I guess like websites kind of are built. They always start from the top and then scroll down. They almost are never built from the bottom going up. And so the same is true for the Y direction. So we've kind of centered this. I think it's a little too high, so we're just going to subtract this by like 30 or I guess add 30 instead of just 32. I think that's still not enough, so we're going to do 28. So one of the game dev recommendations I've seen online is like if you want to see if something changes, what you do is you just double it each time, and then that's a pretty dramatic difference usually. Um, but we're not worrying too much about binary searching right now. I think we're pretty close to dialing it down to the middle. So we don't actually need to worry too much about making sure that this thing is actually attached to the middle of the mouse. I'm just using the mouse because this is easier to see where the center of the screen is without setting up any other guidelines. So now we're going to replace this with 200, and we're going to leave the math in there. And this should be just about in the middle of the screen. I'm not going to bust out a ruler to check that, but I think that's fine. Okay. Now for the sake of being funny, I think it'd be really funny if we were to put a turtle on the other side of this thing and just let the turtle eat. So we want to move. Let's actually. I think it's just about time for us to start making sure we adhere to some clean coding things because we've got a bunch of magic numbers in here that we don't really understand. So let's make sure we can understand this stuff. So 200. This is the value that is like halfway through the screen. And so what we can do is we can just do center is equal to 200. And then we can replace all of these with the word center. And actually, if we wanted to do this thing better, we could just do width divide by 2, and then we don't even have to worry about numbers. And so now we've put... Oh, there's actually something that's called center. So let's not call this center then. Let's call this middle. Okay, cool. So that didn't throw any errors. And so this first one is always the X. So if we want to make sure that the turtle is on the right side of this, what we can do is we could just increase this a little bit more. So I guess let's actually add in a const offset. X offset is equal to 32. Y offset is equal to 25. And so I'm going to move these actually up over here just so we don't have to worry too much about these interfering, or I guess like cluttering things up too much. I'm actually also going to move the text size draw over there. So there we go. This is a little bit easier to read. We're going to add the X offsets. And then we're going to add the Y offsets. And because we made it so that the X offset is negative, we should be fine to just add things. It looks like hands are being thrown. Let's try to see what's going on. Can't access middle before declaration. Ah, that's because this stuff... okay, we're gonna turn these into variables. The reason why it's being very confusing is because setup runs first and then draw runs first, but then everything else runs after all of those things. So what we need to do is we need to actually, we can declare that these variables exist, but then we need to actually define them inside of our setup function. So that's what we're going to do. So I'm going to copy all of these things. I'm going to remove the keyword let in front. And then we're going to chop, chop, chop. Okay, so this should be a little bit nicer. There we go. Cool. So now, if we wanted to add in a distance, a spawn distance for the turtle, we can add this. Let's do maybe like 100. Now it's just chilling on the right side of the screen. Maybe a little bit more. Let's do like 150. Yeah, so we know we have like a range of about 200 from the middle, so I think this is pretty good. So what we're going to be doing is we're going to be changing the rate at which the lettuce um gets eaten by our turtle friend over here. So what we want to do is we're going to want to start animating the lettuce moving. Pretty soon, I will create a new class. We're going to call this the same as what we had before. This is going to be the mover class. We're going to start with a constructor. And what we're going to do is we are going to, let's see. I'm trying to remember how we did the previous one, and I don't remember. Specifically, I'm trying to remember where we actually started doing the draw. So the draw is its own function that's under show. So that means for the constructor, we're pretty much going to be able to do the same thing of doing this dot acceleration is equal to 0.0. This dot, sorry, we can't just set it to 0.0. We need to set it to be a vector. So we're going to do create vector, and then we're going to do 0.0, 0.0. We're going to set it off to be an initial acceleration of 0. Same with the velocity. So if you don't know what the arguments are for velocity, or I guess create vector, the arguments are going to be just the x and the y direction. And the reason why we're using vectors instead of just doing like this dot acceleration y and this dot acceleration x is because this is just an easier, more structured way of doing things. This is a matter of organization so that we don't lose our minds later. And then we're going to do the same thing with vectors, or sorry, positions. Actually, instead of setting it to be 0.0, oh, I guess what we could do is, if we were really funny, hang on, I'm going to resize this so that we have more room on the right side. There we go. That feels a lot nicer. Okay. I think it would be really funny if we made it so that all of the lettuce doesn't necessarily come in from the left side of the screen, but rather that it comes in more, or just like it comes in from anywhere on the screen, but it always homes in on the turtle. Maybe we can put the turtle in the middle. Okay. Um, I'm wondering whether or not it would be easier to actually just like duplicate our old project instead of creating it from scratch. But that's okay. We're gonna create things from scratch since we had some people join the stream a little bit late. Um, let's actually do our show function right over here. What we're going to do is we're going to do show. This is the bit where we can define our text size. And then this is also the bit where we actually draw our lettuce. Okay. We should actually, instead of having it draw in the middle, we actually want to have this draw wherever this dot position is. This dot position dot y. Okay, so something to keep in mind for the people who haven't seen this function before, the this dots, or I guess vectors come with at least two attributes, technically at least three. It always comes with an x, a y, and a z. And so if we can access those by just doing the dots. The reason why we need to use a vector instead of just creating our own object that just has just the x, just the y, and just the z is because these create vectors also come with some functions that allow us to do vector math. And that is really useful for when we want to do crazier, I guess, like animations that are more simulated e. um, but yeah. Anyway, we're not going to be able to test anything just yet because we don't have an update function. So let's make sure we have an update function. And so this update function is going to be the thing that actually does our math for us. Thankfully, the math isn't going to be too crazy because we're letting the computer do the hard work here. Basically, what we're going to do is we're going to do this dot velocity, and then we're going to add the acceleration. This dot position dot add this dot velocity. Now, previously, we also kind of clamped this with a limit function to make sure that the acceleration didn't go too crazy. We could do that, but I think it would be kind of funny to just like have a bunch of lettuce just going straight to our friendly neighborhood turtle really, really fast. um, so yeah, we're gonna do something like that. I'm actually going to chop this off. We're just gonna let our turtle be in the middle. Oh, he's so small. Okay, let's actually move our text size back over here. All right. So our turtle is a more respectable size again. Okay, so we've got updates, we've got show, we've got constructor. The last function for us to make here is to make the check, I guess like to make sure that the lettuce gets eaten by the turtle and then just like respawns somewhere on the screen. So we can do is check eaten. And then inside here, we're just going to check to see if the lettuce is right wherever this bit is, middle and offsets. But let's see. Do we need to do anything with our offsets to make sure that the lettuce actually looks like it's in the middle of the screen? Yes, I think we do. We want to make sure that the lettuce actually kind of lines up with this. So I'm actually going to take this and we are going to set the, I guess like emoji middle. Emoji middle X. Emoji middle Y. There we go. I'm starting to feel like this is against clean code practices, but at this stage, I think that's fine. Emoji middle X is equal to middle plus X offsets. Middle emoji middle Y is equal to middle plus Y offsets. So now we could actually replace this with the emoji middle X, emoji middle Y. So let's just check to make sure it's still in the middle. There we go. Totally is. So now what we want to do is we want to make sure that the lettuce can move in the direction of our turtle friend. Now let's actually give this an initial velocity of going towards the middle of the screen. We are going to need to figure out how to make sure that that actually goes. Because if we just do like a 1.0, 1.0, and then let's go ahead and we don't have to worry about check eaten right now. What we're going to do is I'm going to hide the setup function. We're going to create a new mover. Let's define this outside. We're going to define this inside setup. I will declare the variable first. Let lettuce is equal, nope, let lettuce exist. Lettuce is equal to a new mover. Lettuce dot update. Lettuce dot show. Okay, so Bam. We've got lettuce floating around the screen now, which is good. The hard part is we need to figure out how to create a vector to make sure that this thing goes towards the middle, even if it spawns from a different direction. And so that means what we're going to need to do is we're going to need to do some vector subtraction, I think. So here is one thing we can try doing. We can try setting up the middle vector. Middle vector is equal to create vector 0.0, I guess 0 and 0. I don't think JavaScript's going to complain too much about that. And then what we can do is we can see if we can set the velocity to be equal to this dot velocity. Let's see. Let me make sure I'm using the right thing here. Subtraction. So if we have a vector that is sitting in the middle and we want to figure out how to get to it from this direction, from somewhere else, we need to subtract the two vectors, I believe. This is where my math intuition might fail me. So if there's somebody in the stream who has a better understanding of that, feel free to hop in and let me know I'm doing something completely goofy. But I'm pretty sure all we need to do is, let's see. I'm trying to remember how this works. All right, we're going to assume that we're going to get this right, I believe. So we're going to hide out the acceleration bit for now and do this dot velocity dot subtract middle vector. Okay, I don't know why I was expecting that to do anything. Here's what we can try doing. We can try setting this to be 0.0. This dot update. This dot add velocity. So because the vector is actually 0.0, it's not going to move anywhere. Okay, that makes sense. What we actually wanted to do is we wanted to set the middle vector to be in the middle of the screen. So let's actually set this to be 200 and 200. Let's see if that changes anything. Okay, I think that might have moved things too fast. Let's do some copy pastas, yeah? Height divide by 2, height divide by width divide by 2, height divide by 2. That's going to be going to the center. Okay. And then subtract the center. We don't want to be multiplying or dividing it. I'm pretty sure subtraction is the way we need to do it. The negative version of the scalar becomes -3. Subtraction is the same as addition, only it's treated as a negative version of itself. To actually solve the subtraction, take the difference of the components. I suspect that our velocity might actually be going in the opposite direction, or our vector. So maybe instead of this, maybe what we're supposed to do is this dot position dot subtract this. I guess we'll just take the middle vector. And then we still needs to add that. No. My critical thinking skills are not up to par today. This dot sub middle vector. Okay, I think we're getting a little far away from the original thing. Let's think about this. I'm gonna bring out the whiteboard. So we've got a frame that exists. This is our canvas. All right. And then we've got a point that's sitting right in the middle. Okay. And then we've got, let's just do a rectangle for now. Just floating around over here. So then if we want this to point to this, that is the velocity the direction. We need to change the direction. So we need to take the normal of our velocity so we can find the direction. And then once we have the direction, we need to make sure it points to the middle. So how can we make it points to the middle? I know how to make it fly diagonally. I guess. Hmm. Okay, so let's actually. Okay. We know how to make it fly diagonally. I'm going to make a few of these. Just so we can get a sense for what the vectors should be. Okay, so in the top left, we know that the vector needs to be 1.0, 1.0. So then if we wanted to come in from the opposite direction, we would know that this needs to be negative, negative. And then so if it needed to be up here, it needs to be negative first and then positive. And then if it needed to be over here, then it needed to be positive first and then negative. Let's make sure that that makes sense. So right now, yeah. So then if we were to set this with the initial position to be 1.0, whoops, whoops. Wait, wait. Why isn't it that the position is starting off in a different location? Oh, maybe it's because we need to actually do the height. Yeah, there we go. Okay, that makes sense. Okay, so we need to so the position is I guess like wait, did we get that direction right? Okay, so if it is negative for the x value, then yeah, it will float in from the right side. And the other coordinates needs to be the heights. I guess technically speaking, the initial position doesn't really matter if it's 1 or 0. Because this is 0, 0. This is technically 0 height, and this should have been width, actually. And then this is width, height. Oy. So what we need to do is we need to make sure that we have something that moves towards the middle. Okay. So then, oh, okay. Okay, I think I figured it out. What we need to do is we need to have a map. So the map function is something that looks like this, where we take in our value, the min value, max value, and then we put in the min range, max range. So what we need to do is we need to map where the current coordinates of whatever object it is that we spawned. We need to take that. So I guess that would be okay, we would need to do this for both the x and the y, technically. So we can take the x value, and that would be a difference between 0 and then the width. And then we would go for the min range. It would be from, I guess, negative 1.0 to 1.0. Okay, and then we just do the same exact thing for the y. And then we change that to height. And I think that should make it so that everything, no matter where it is on the screen, is going to go back towards the middle. So using this information, I'm going to copy this over. I'm going to go back over here, and this is so funny to watch. We're going to use this information that we just discovered. And my pea-sized brain is going to completely forget how to do this. Okay, so no subtraction. All right, we've got our vector math. Yes, with the acceleration. Okay, that's fair. We've got the position.add. Okay, that's fair. So the constructor is going to create a value. I guess what needs to come first? What needs to come first is the position. So let's move this. Whoop. Let's move the position to the very top. So this can be any value between, I guess, actually, let's set this up as a variable up here. So let's x position is equal to random between 0 to height. No, width, because this is position. Let y position is equal to random 0 to height. And then we can do x position, y position. And then, okay, so now we've got it spawning in completely random places. This is good. Now what we need to do is we need to take these positions, and then we need to map it. So then let's x velocity is equal to map x 0 to width negative 1.0 to 1.0. And then we're going to do the same thing with y. Position. Okay, that doesn't do anything yet because we haven't actually changed this to grab these other values. Oh, I didn't need it on acceleration. I needed it on velocity. Okay, so it looks like it's going in the opposite direction. So let's actually flip this. Okay, I am so happy that I figured that out. Okay, so we figured out how to make it so that the velocity makes it so that it's always zooming, like going in towards the middle. So now, if we were to do our check eaten, all we need to do is check to see if it's gone through the middle. And so the middle vector, I guess we also have the emoji middles, huh? Oh, we should be doing, oh, I don't actually need this anymore because I thought we needed it, but we didn't actually. Emoji X, okay, so all we need to do is we need to check to see if this dot position dot x is equal to emoji middle x. And the same is true for the y. And then so we're going to set the speed to be equal to mid x mid const y mid. If x mid or y mid, I guess x mid and y mid. So then x mid, y mid. Then we're going to just reset the. Oh, we would need to reset both the position and the accelerate, or and the velocity. So I guess what we could do is we can yoink this. Wonder if there's a more, like a nicer way of doing this. I want to make like a helper function for this, so I can just call that instead. Let's take that out. And let's make a spawn function. And then what we can do is we can, instead of doing that, we can run this dot spawn. Okay, so that still works. And then so what we would need to do is we just run this dot spawn. Ah, so I just realized that this is actually never going to hit the true middle because we're not going towards the middle right now. We're just getting really close to it. So instead of worrying about the X emoji blah blah blahs, here's what I'm gonna do. I'm gonna put this back over here. Take this, put this back over here. Now we're going to delete these, eat, delete. We don't need you anymore. Okay, let's make sure this still runs. It still runs. Let's check to see if it's just in the middle. So that would be whoop, width divided by 2, height divided by 2. Ah, we're not calling check eaten anywhere. That's not what we need. Hmm. Let's just... Why is it constantly spawning? Okay, let's remove this. Oh, now it's always spawning in the middle. Is it the way that I did this spawn function? No. That only happens when I ran check eaten. Yeah, so check eaten is severely forked. Because as soon as I add that, that's when everything breaks. Okay, let's check to see how the previous one had done check edges. Let's see where it gets called. Yeah, it gets called right after the update and before the show, which is pretty much how we're doing it as well. Because there's the update and there's the show. But for some reason, it gets really spazzy. Ooh. Okay. Hmm. Indeed. I'm trying to figure out whether or not we should cut our losses or just continue working on the the rest of the exercises. Because technically speaking, we didn't even get to the acceleration bits to actually, learning how to do the anchoring and stuff. I am pretty satisfied with the fact that we were able to make the lettuce happen, though. I guess the easiest thing for us to do is to just yoink our check edges function and then just run that instead, and then we'll just delete it, and then it'll look like our turtle is just missing um, all of the lettuce. Let's see. So instead of this, we do check edges. So let's see what happens when the lettuce goes off screen. Right, it would just spawn on the other side. What we could do is we could make it spawn from the same place that we had it before. But in order for us to make it spawn in the same place that we had it before, we would have to have had it keep track of where the previous position was. So I would much rather just respawn it. So here's what we can do. We can do const x max is equal to this, const x min is equal to this, x max or x min. And then we just do this dot spawn. And then we do the same thing for y. Okay, there we go. I guess we can also do y max, y min. Let's see what happens. Okay, so it does actually respawn. So now all we need to do is just change it so that whenever the x is, I guess, like in between a specific range of wherever our turtle is, let's actually start by, we can we can figure out where our turtle is by just like drawing a box and just seeing if we could get the turtle like boundary box, like the collision box right around this. So let's go ahead and do that. We're going to do a rectangle. We'll make this size 64, which is the same size as our turtle. And then we're going to put this right in the middle. But of course, we remember that the rectangles actually don't spawn quite in the middle. So what we need to do is we need to subtract by the width of the box and then add by the width of the box. Maybe not add. We're going to subtract as well over here. Or I guess it should be half the size of the box. Kind of. Well, I guess what we should do is we can just do the y offsets because we have that. Subtract the y offsets. Okay, there we go. So now we have a good boundary box. Woo! Okay, so now what we're going to do is we're going to take these values and just check to see if the position, our position.x is in this range. And if it is, then we're going to get rid of it. Otherwise, we're going to just let it exist and continue floating around. So we've got x min. Are you asking me to print hello world, or are you just saying hello worlds to the chat? Either way, welcome to the channel, or welcome to the stream. Okay. So we need to make sure that the x is less than, not the width, but we can do less than half and then plus the x offset. Okay, let's just check to see if that works. Okay. There we go. There we go. Okay, and then we don't really have to worry about the x min anymore because we're not going to be worrying about it floating off into the other direction. So we can chop that out. So I would say we can actually do the same thing with this other side. And then I think we also just add the y offset. Yeah. And then we chop off the min. So let's see what that looks like. Okay, we're looking pretty good. I'm going to remove the turtle, or sorry, the box. Okay, so next thing is we should also make sure that the random positions under the spawn doesn't actually spawn within the radius of the turtle. So let's make sure that, let's see, that it is either, we can have another random variable here. Let's, oh, I'm going to set this to be const, just so we don't accidentally tweak this later. And then we can do coin flip, for the lack of a better word. We're going to do 0 to 1. Thank you. Thank you. We try. We try to make things cute. But right now it's kind of spastic, so it's not super cute yet. Okay. So we've got it. We're going to do a random coin flip, and I'll explain why I want to have this. The reason why is because I want to make it so that it either picks like a random X or Y, because I want to make sure that it spawns either on, I guess, like one of these corners over here instead of spawning in the middle. We want it to be spawning from the edges, which means that one thing is always going to be full, or I guess we should be doing this on the range of 4. So I guess we can actually just do this as direction. Okay. Yes, it is eaten randomly. Thankfully, the lettuce grows at the rate at which the turtle can eat. Actually, I think as just because this makes for a fun screensaver on the side, let's actually just take a quick break from what is we were doing earlier and spawn in some more lettuce. So here's what we're going to do. We're going to make lettuces. And we're going to go ahead and initialize a whole bunch of lettuce. So we're going to do for let I is equal to 0, I is less than. I guess let's do 10 for now. And then if we think our turtle is a very hungry turtle, we can add more. We can do lettuces I is equal to new mover. I guess we should actually just call this lettuce because it's always going to be a lettuce. New lettuce. And then inside our draw, what we can do is for let I is equal to 0, I is less than 10, I plus plus. Pop this in here. There we go. And then we're going to set lettuce is equal to lettuces I. And then we should have a whole bunch of things going on. That didn't quite work. Lettuces is equal to an array. Okay, so I'm realizing that we have a bit of a problem here. They're all spawning in the same quadrant mostly. This is still pretty entertaining. But yeah. Oh, I see we have an opinion in the chat. Pray tell, what is your opinion? But yeah. I think let's roll with that for now while we try to figure out what the deal is for the spawn situation. So if the direction is equal to 0, let's give him a banana too. Okay, here. Let's actually add is lettuce. And now we'll make it so that there's a coin flip that happens, determine whether or not it's going to create lettuce. And let's see. We need to make sure that this happens wherever the show is. I guess, yeah, we would need to handle this before it gets to the show method. So the show method, we could make it so that this has an argument. Because right now the show method runs here. So we could pass it information. Lettuce.update. We don't want it to be under updates. We don't want it to be under check edges. We only want it to happen if it spawns. So I guess what we can do is we can create a new thing, which is called this dots. We're going to call this sprite. And we're going to set it to be initially the lettuce right here. Okay, so then we can change this to be this dot sprite. There we go. That broke for a reason because I had that if statement. All right. Okay, next thing is we want to make it so that when it spawns, there is a random chance of it being lettuce and a random chance of it being something else. So let's handle this logic first. Is lettuce is random, and then whatever the result of the lettuce is, we will set it, if it is lettuce, then we will set the sprites to be this favorite thing. Otherwise, we can set it this dot sprite is equal to, and then we can have our banana. So let's see how that works. I don't think it's working. Perhaps it's because we're not running the spawn as often as we should be? Question mark? Oh, that's because this needs to be true or false. There we go. Wow, that's a lot of bananas. Well, I guess I should probably do that. Random I, rand I, p5 random integer. I suspect it's trying to select a random number between 0 and 1. Get random coordinates between 0 and 1. I want it to be an integer though. So does it give us floats or just integers? Because that is an alarming amount of bananas. Let's actually just do a console log on both. I guess I should set this to be random first. Both the result of is lettuce as well as the result of this dot sprite. Well, actually, I'm pretty sure we know what the result of the sprite is going to be. We just need to see what the lettuce is. Yeah, so it's definitely just a value between 0 and 1. So here's what we need to do then. We can just do round. I think that's going to let us do that. Yeah, so now it's 0 or 1. Cool. Yes, I'm very happy to be able to enlighten your opinion. And also thank you for the compliments. All right. Let's see what else we have to do. Well, we still need to fix this whole spawning situation. So I suspect what's happening is as soon as it spawns outside of these areas, it just absolutely gets obliterated, which is why we need to add an like a min value probably. Because yeah, if the x is greater than the width, if it spawns over here, that's why it just gets immediately deleted. So I guess what we need to do is we need to do a check to make sure that um let's see. We need to do a I guess technically, yeah, that is the max. And then we want to make sure that I guess okay. We're gonna call this x left, so this is the left side of the turtle, and then we're gonna have this something on the x right. So this is where the position is greater than the width. Okay. Which is totally fine. It's fine for it to be greater than the width. What do we need? What do we want to happen if it's greater than the width? Oh, actually, what we need is for this to be an and. Let's actually just see if this changes anything. Okay, so now none of them are being deleted. So what we need to do is we need to make sure that it goes inside. If it's inside a very specific range, then we do something with it. Also, none of these are despawning. Okay. So if it is inside... max... Oh, okay. So here's what we need to do. We need to actually combine the x and the y. Big surprise. To make sure that if it is within the x and the y coordinate that's closest to the middle. So, hang on. Oh, I can feel the hints of the idea. Um, Maybe I need the whiteboard. I'm gonna use the whiteboard. Maybe not. I think we can figure this out. Okay. So, x range. It can't. If the x and the y is greater than half, then we know that it needs to be respawned. But it can also spawn on the other side. And so if it is greater than the x and the y, you know what we can do? We can actually just find the distance between where it currently is and where the middle is, and then just do that instead. So I guess okay. So here, let's do this. X distance. I'm gonna set this up in a new area actually. Okay, x distance is equal to this dot position dot x minus the width divided by 2 plus the x offset. I guess I should also just set that to be its own thing. The middle x middle is equal to width divided by 2 plus the x offsets. Const y mid is equal to the height divided by 2 plus the y offsets. Then we can do y mid const y distance is equal to this dot position dot y minus, oh, this should have been x mid. This is now y mid. Okay, so then as soon as this distance is less than 10, I want to say, x range is equal to x distance is less than 10, const y range is equal to y distance is less than 10, then we can do x range and y range, and then we can make it respawn. Okay, I think 10 is a bit too small, so let's do 64 and 64. Okay, 64 seems a little much, so let's do 32 and 32. Okay, cool. That is pretty close to what we want. The next thing is we want to make sure that these things all spawn like on the outside range, but we only have 2 minutes. I don't think I'm gonna have time to do that. So here's what we're going to do. Um, if let's see, let's actually just quickly scroll through here to see if there's anything else we could have done. I think the next exercise, yes, making it accelerate towards the mouse. Oh, that is really cool, actually. Okay. Um, let's see. If we remember next time I run this stream, I want somebody in chats to be like, we want the healthy turtle. And then we can continue working on this. Otherwise, we'll probably be covering a new chapter. We'll do a quick recap on things that we covered inside the acceleration and vectors chapter. And then, yeah, I don't know that I'll be streaming next month for API week because I'm going to be coming back from a hackathon. Like the weekend before, and I'm gonna be really tired, especially because I'm still also doing schoolwork. So that's gonna be probably a bit much for me. Maybe in December, I will be back for another stream. If you all can remember that far, definitely do say hi. um, let's see what else. Okay, well, here's a feedback form. If you want to let the team know that you want to see more turtles and lettuce and bananas, do let me know and let my boss know. That always helps a lot. And otherwise, I will actually let's save this right now so I don't forget to share it. GHW vector turtle. And then I'll drop this in the Discord announcement as a reply to my previous one. And yeah, I want you all to have a fantastic day. Eat your vegetables and fruits today. Stay healthy. Stay hydrated. And I think the very next stream is going to be the Today in Global Hack Week for the final day. Thank you so much for tuning in today. I will hope to see you all very, very soon. All right, take care, everybody. Bye bye. And thank you for the lovely comments. I appreciate it. All right, bye.